As Shakespeare said, would an average by any other name give an accurate representation of the central tendency of your data? I'm paraphrasing, of course, but that's what we're talking about today. Averages is what you probably are used to calling these things, but we're going to change that a little bit. We're going to introduce you to the concept of the mean and the median. We're going to discuss the concepts of central tendency and dispersion when you look at data, and we're going to improve your blackjack game a little bit. So if you've never played blackjack, stay tuned. In blackjack, your goal is to get as close to 21 as possible without going over. If you go over, you lose. If the dealer gets a higher total than you, you lose. And as you probably know, the house always has an edge. But they don't always win. Any of you who have played blackjack will know that some hands you win and some hands you lose. Sometimes you even walk away with more money than you started with. But the house has the edge. Over the long run, they'll always make money. But there's something special about blackjack as a casino game. Statistically, blackjack has one of the highest standard deviations of returns of any casino game. What the heck does that mean? Well, by the end of this session, you'll know, and more importantly, you'll know how it applies to medical science. So what do I mean when I talk about blackjack winnings? Okay, imagine you're playing blackjack at $10 a hand, and you're playing one hand per minute. How much do you think you'll win over the course of an hour? Everyone kind of get a number in your head. Okay, now some of you might think, oh, well, I'll probably win $100 over the course of the hour. And some of you might say, oh, knowing me, I'd lose $100 over the course of an hour. And in fact, we can model this statistically just using mathematics to determine what the most common outcome is. And that's what this graph is. This is a type of graph called a histogram, and I really like it. What it shows you is the relative frequency of different outcomes of a repeated measurement, okay? And so what you see on the x-axis here is the amount of money you would win. And the y-axis just tells you how common it is, with higher being more common. And what you can see is that the peak of this histogram is just to the left of 0, right? So just a little bit less than 0. People tend to lose more than they win at blackjack, and that's, of course, why casinos stay in business. But you can see there's a really big spread here, right? It goes all the way down to negative $200, loss of $200, and all the way up to $200. And in fact, it's that spread that is what makes blackjack so exciting to play. Now, what do you notice about this data when you look at it? Well, this is normal data. Remember our last video, right? So this is a nice bell-shaped curve. It's normal. And I didn't tell you last time, but there's something special about normal data. Normal data can be expressed with just two numbers. This entire constellation of data can be expressed with two numbers. One is the mean, and one is the standard deviation. Now, in this simulation of blackjack, the mean loss was $3. So on average, your average person is going to lose $3 playing a game of blackjack for an hour, betting $10 a hand, one hand per minute. You'll lose about $3. Not too bad for an hour's entertainment, right? But the standard deviation is $85. That is a measure of dispersion, how wide that ranges. And you can see that the standard deviation is plus or minus $85 here. Now, one standard deviation on either side of the mean is about 2/3 of the population. And two standard deviations is about 95% of people. And that's just sort of a standard rule of thumb for how you might interpret this, which is to say that if you sit down to play blackjack, you'll probably lose something other than negative $3. You might lose as much as $85, or you might win as much as $85, or you could even be further outside of that normal distribution. You could be one of these people that just got really lucky or really unlucky. But that standard deviation is huge compared to the mean loss, and that's what makes blackjack so fun, because the casino only cares really about the mean, right? The casino says, on average, we've got tons of people coming through here. They're all losing $3 an hour. We're going to make money that way. You don't care about the mean. You don't care what happens on average to 100 people. You only care about you. And you have this chance to make all this money, and that's what keeps you coming back to the table. If you lost $3 an hour on average, but the standard deviation was plus or minus $1, well, that wouldn't be a very fun game, because it would be a kind of game where everyone just sort of slowly loses every single hand, and you maybe lose 5 cents every single hand. That's not exciting. You want that big swing, and that's what blackjack gives you. That's the standard deviation. Okay. Now, medical studies work the same way. At least they present the same data, but they almost never show you histograms. Instead, they just show you those two numbers. that I told you you can use to describe a normal distribution. So they use the mean and the standard deviation. And here's a study that randomized patients with back pain to opioid medication to control the pain versus non-opioid medication. And I'm just showing you the ages of these patients. And what you can see is that the study reports the mean age in each group. One group had a mean age of 56.8 years and one 59.7 years. And then in parentheses, it gives you the standard deviation. What's the kind of range in there? And remember, 2/3 of people will be one standard deviation above or below that mean. So that just gives you a sense of kind of how wide the range of ages were in this group. If that standard deviation was only 1 year, we'd say, oh my gosh, they only enrolled people who were like 56 years old. That's a very specific study, right? So that gives you a sense of the range. This is what the histograms might look like, but we're usually not provided that data. We're going to assume that they're normal-ish in distribution, and in fact, both of these histograms would give you similar means and standard deviations when you analyze them. By the way, in this study, the non-opioid pain control did better than the opioid pain control in terms of controlling back pain. Go figure. Okay, but remember, not all data is normal. So what about abnormal data? Remember our data on US population by age? It does not look like a bell-shaped curve at all. It looks like there's a big tail off here on the right-hand side because we have very few people that are living into their 90s or 100s. Now, if you were to express this with the mean and standard deviation, it wouldn't really make much sense because that's really just for data that falls into that nice bell-shaped curve. So what do we do when we have weird-looking data like this? Well, we have another metric called the median. The median is quite simply the value that divides all of your population perfectly in half. So let's take a look at a common thing we might talk about, which is median household income in the United States. Okay, so it will surprise none of you that the income distribution in the United States is not normally distributed. In fact, there is a small percentage of people who make so much money, it has a really strong right skew. So if you look at the mean income, that's the arithmetic average, right? You just add up all the incomes and divide by the number of incomes. If you look at the mean income in the US, you see it's around $72,000. But if you assume that the average American makes $72,000 a year, you are quite a bit off, my friend. Because if we find the median, which is the value that separates us into the top 50% and the bottom 50%, that number is $53,657. And you can see in this graph that the median income over time in the US was increasing for average families right up until that financial disaster in around 2000, the late 2000s, and then started declining and maybe is starting to barely pick up again. So when the data is non-normal, you're going to look for a median. Okay, so I gave you two measures of central tendency. The mean, which is how you used to do averages when you were in grade school, and then the median, which is defined just as that value that divides the population in half. Well, we can show both, and in fact, in that opioid study, they give you both. They give you the mean age, and they give you the median age. But note the difference in the parentheses, okay? So we have a standard deviation, which I explain, and then we have this thing called the IQR. Stands for interquartile range. And you can see that it's not one number, it's actually two numbers here. So the median age in the opioid group was 59.5 years, and the interquartile range was from 46.5 to 67 years. So what does that mean? Well, take a look at this little picture. This is, imagine we took a test. I gave everyone who's watching this course a test, and everyone got scores, and the scores might not be normally distributed. There might be some people with very high scores and some people with very low scores. It might not be a bell-shaped curve at all, okay? But we could very easily find the median, right? The median is just the value that divides the population in half. And in this case, the median was 71%. Okay, 50% of people did better than 71% on the test. 50% of people did worse than 71% on the test. Well, we can do the exact same thing with the lower half and the upper half of the data. We can split that in half to essentially say, okay, a quarter of people did worse than this, and then a quarter of people did better than this. That forms the interquartile range. So you can see the interquartile range here goes from 64 to 77. So you have a measure of central tendency, the median, and a measure of dispersion, the interquartile range, defined entirely different than the mean and standard deviation, but conveying very similar ideas behind the data, which is, kind of how much the observed central value sort of varies as we look across the population. So what are our take-home points here? Now, much of statistics involves taking raw data and summarizing it using math, which is why the ability to express a normal distribution with only two numbers, the mean and standard deviation, is so powerful. The term average is really not specific enough, so we really want to discuss whether something is a mean or a median. Now, if the authors are using means and standard deviations, they are giving you a wink and a nudge that the data they're describing is normal, bell-shaped, at least they should be. If they're instead giving you median and interquartile ranges, they're telling you that this data was not normally distributed. And remember, that's fine, but different statistical tests are used for the different types of data. And to be honest, most data, like most people, is not normal. Okay, it's not normally distributed. So you're going to see a lot of medians and interquartile ranges in medical studies. And at this point, you shouldn't be too confused as to what those are. Thanks a lot.